Okay, let us start the session then. Is the screen visible to everybody?
Yes, excuse me.
And am I audible, right?
Yeah, you are.
Okay, so since the meeting screen won't be visible to me, and if any of you find anybody is waiting in the lobby, just please let me know, interrupt and let me know so that I can let the person in. Sorry. Mm, good evening, everyone. My name is Abhik Deb, and I welcome all of you to the fifth live session of the course Concepts of Thermodynamics, which is being taken by Professors Dr. Suman Chakravarti and Dr. Aditya Bandyopadhyay at IIT Kharagpur. As in for myself, I am a Prime Minister's Research Fellow in the Department of Mechanical Engineering at Indian Institute of Science, Bangalore, and I shall be dealing mostly with the live sessions wherein we will solve some of the problems related to the concepts that have been discussed in the previous week theory classes, so that some of the doubts can be cleared. So if any of you has any doubt related to any of the problems that will be solved in the session today, you can directly interrupt and ask, or you can type in the chat box, or you can also ask in the discussion forum so that they can be answered. But I would request you to ask directly in the session itself so that it can be cleared properly here. And I request all of you to be present every Friday from 6 to 7 p.m. to make this program a success. So let us move on to the problems. Today we will be mm, dealing with the problems related to the steady flow energy equation of thermodynamics. So most of the problems are related to that, quite simple, but they will help you in clearing the concepts related to the application of this equation. So let us start. Mm, So the question number one, a nozzle receives 0.1 kg per second of steam at 1 megapascal and 400 degrees Celsius with negligible kinetic energy. The exit is at 500 kPa and 350 degrees Celsius and the flow is adiabatic. We have to determine the nozzle exit velocity. Okay, so there are two conditions. One is the inlet of the nozzle and one is the exit of the nozzle. So at inlet of the nozzle, that is at 1 megapascal pressure and 400 degrees Celsius. This is the property table of superheated water, and at 1 megapascal and 400 degrees Celsius we can see that the enthalpy of water or steam in this case will be this one. So we can write it as I for inlet, that is 3264.5 kilojoule per kg. This is the specific enthalpy. Okay. Mm, Then again at exit of the nozzle, that is at 500 kPa and 350 degrees Celsius. The 500 kPa is 0.5 megapascal, right? So at 0.5 megapascal and 350 degrees Celsius, the enthalpy value is given as this one. So H exit, that is 3168.1 kilojoule per kg. Now, if we write the steady flow energy equation, flow energy equation, will be referring to it as SFEE in the rest of the session. So what is the steady flow energy equation? This is basically an energy balance for a closed system in which there is a this is the energy balance for an open system in which there is a flow of material. um, there is a flow of mass, but it is a steady, that is there is no buildup of energy or mass within the system. So if we write the steady flow energy equation, G V E square by 2 plus G Z E. So what are the salient terms here? This is the heat that is transferred to the system, that is it is heat transferred into the system. This is the the mass multiplied by these specific values give the flow energy related to the mass that is coming into the system, that is at the inlet. This is the work done by the system, that is what is the work done leaving the system, that is work done by the system. And this is the flow energy of the mass that is leaving the system, that is at the exit. So here it is said that the flow is adiabatic, that is Q is 0. So here this Q value, this is 0. Okay, and there is negligible kinetic energy, that is V1 Vi is equal to Ve is equal to 0. Vi and Vi squared by 2, this is the this refers to the kinetic energy, and this refers to the potential energy at the inlet, and these are the values at the exit. So it is said that it moves with negligible kinetic energy, so Vi and Ve both will be nearly equal to 0. And if we neglect the changes in potential energy. Okay, so what this steady flow energy equation, and also there is no flow work, there is no moving surface here, right? This is simply a nozzle, so there is no moving surface, so also the work output of the system is also 0. Okay, so what does this steady flow energy equation become? This becomes 0. These terms are neglected. This term also becomes 0. Sorry, it enters the system with negligible kinetic energy, so there is a this thing, it enters the system, so there will be only at the inlet it will be 0. So we have to determine what is the exit nozzle velocity. So the equation becomes Hi equals to He plus Ve square by 2. So Ve is actually equal to under root of 2 times Hi minus He. Okay, so if we put in these values, 3264.5 minus 3168.1, so this comes out to be equal to 439.08 meter per second. So this is the option D. There is a slight change in the value because the table that has been used in the that had been used uh, in the solution of this problem, where I have taken this problem, the table is a bit different, the property table, so there is a slight change in the value. So the answer will be
Battery is discharging.
option number D, that is 438.7 meter per second. Okay, so was this clear to everybody? If there is a doubt, please ask. So no queries, I guess. Okay, so then let me move on to the next problem. So this is a continuation of the previous problem, that is so in the previous problem we have to find the nozzle exit area. So for this, see, at the nozzle exit, that is at 500 kPa and 350 degrees Celsius, from the table we can find that the specific volume is this value, 0.57015. So the specific volume at the exit is 0.57015. So we know that the mass will remain constant at both the inlet and the exit. That is, we have, that is, mass flow rate at the inlet is equal to mass flow rate at the exit. It is a steady flow system. So the nozzle receives 0.1 kg per second of steam. So we can essentially say that the mass flow rate at the exit will also be 0.1 kg per second. So what can we write it as? This is area at the exit, velocity at the exit, this is the volume flow rate, and if we multiply it by the density of the steam at the exit, then it will give the mass flow rate at the exit. So this is 0.1. Now AEBE, and this what is the density? Density is 1 upon the specific volume. So this is 0.1. So nozzle exit area we have to determine. So this is AE is equal to 0.1 into VE divided by this VE. This is the specific volume, this is the velocity. Be careful with this. So 0.1, 0.57015, and velocity is, we have found 439.08. 439.08. So the area will come out as 0.000129. This will be in meter square. Okay, so all these units are in SI units, so this will be in meter square. So we can write it as 1.29 centimeter square. That is area of nozzle at exit is this value. Okay, so so is it clear to everybody?
Yes, sir.
Okay, so if there is any doubt, please ask. Okay, so let me move on to the next problem. Okay, so the figure shows a diffuser. So diffuser is what? This is the opposite of a nozzle. You know, the nozzle is like this, that is, it has a decreasing cross sectional area. Okay, and diffuser has an increasing cross sectional area. So it can be a gradual increase, I mean it can be a tapered section, or it can be a section like this in which the variation, the increase in area is not constant. So anyway, let us move to the problem. The diffuser as shown in the figure below has an air entering at 100 kilopascal and 300 Kelvin with a velocity of 200 meter per second, and the inlet cross sectional area of the diffuser is 100 millimeter square. So the inlet conditions are almost all given, and the at the exit the area of the nozzle becomes 860 millimeter square, and the exit velocity is 20 meter per second. We have to determine what is the exit pressure of air. So let us start with the steady flow energy equation here. If we write the steady flow energy equation, that is Q dot m hi plus vi square by 2 plus gzi is equal to w plus m dot he plus ve square by 2 plus gze. Okay, so here for a diffuser, both the heat transfer and the work done by the system are 0. Okay, so here these values, this is 0, this is also 0, and if we neglect the potential and we neglect the changes in potential energy, okay, so essentially what happens, therefore, so this is 0, this is 0, m and m gets cancelled, and we neglect the changes in the potential energy. So hi plus vi square by 2 is equal to he plus ve square by 2. Okay, so we can say that hi minus he, hi minus he will be equal to ve square minus vi square by 2. So this will be what? It has an exit velocity of 20, so 20 square minus inlet is 200, so 200 square by 2, and this comes out to be 19800. Okay, so now this value, considering that the specific heat of air remains constant at this within this temperature range, that is from 300 Kelvin to the exit temperature, we can consider that for a constant specific heat it will be Cp Ti minus Te is equal to 19800. Okay, so Te will be equal to Ti plus 19800 by Cp. Now Cp for air we are taking it as 1004 as a constant value, kilojoule per kg Kelvin. Sorry, this is joule per kg Kelvin. Joule per kg Kelvin. So this is 1004. So if we put in the values, that is 300 plus 19800 by 1004, and it comes out to be equal to 319.72 Kelvin. Okay, so I hope it is clear till this one. Then we will move on to the next part. So after we know the exit temperature, for exit temperature of air is 319.72 Kelvin. Okay, so now since we know the exit temperature, now we also know that the whatever mass is coming in will be leaving the system at the exit. Since it is a steady system, so there will be no mass built up in the system. So for a steady system now, this one is equal to the mass flow rate at the exit. So we can write it as, from for considering air to be an ideal gas, we can write pressure at the inlet, volume at the inlet, volume flow rate at the inlet by R, and temperature at the inlet is equal to pressure at the exit, volume flow rate at the exit, R, and temperature at the exit. Now we can write the volume flow rate as area at the inlet and the velocity at the inlet. Okay, by R and R gets cancelled, so Ti, this is Pe, this is AEVE. Similarly, the area and the velocity gives the volume flow rate at the exit, and this is Te. So we have to determine what is the exit pressure. So exit pressure is equal to inlet pressure multiplied by AI by AE multiplied by VI by VE multiplied by TE by TI. So if we put in the values, the inlet pressure is 100 kPa. So let me keep it as 100 kPa. Area at the inlet is 100 and the area at the exit is 860. The inlet is 100 and the area at the exit is 860. Since both the units are same, so we did not convert it to SI units because they will be getting cancelled. I mean, numerator denominator units will get cancelled in each of these cases. And the velocities, so the inlet velocity is 200 and the exit is 20. So this is 200 by 20 and this is the inlet exit temperature that we have found, 319.72, and this is 300. Okay, so the pressure will come out to be 123.92. Therefore the exit pressure of air is 123.92 kPa. So this is the answer. Okay. So I hope it is clear to everybody. Then is it clear to everybody?
Yes, sir.
Okay. Okay. Thanks for the response. We will next move on to the next problem now. Okay. So the next point is the next process is essentially a throttling process. Okay. So it is R134A. Can anybody say what is R134A? Anybody? You can please unmute and say if you know.
Hello, sir.
Yeah.
It is a type of refrigerant.
Okay. Yeah. So it is. Do you know what its name is?
I think it should be ammonia.
No, no, not ammonia. So it is basically tetrafluoroethane and ammonia. No, no, it is not ammonia.
Okay.
So it is basically R134A. If you, has the nomenclature of refrigerants been taught to you yet?
No, sir. Sorry, sir.
Okay, so just a minute. Actually, when you come to know of the nomenclature of refrigerants, I don't know if it is. I mean, it will probably be taught in the future classes. It will be taught how you will name these refrigerants. It is one of the most commonly used. It was one of the most commonly used refrigerants, but because it is a ozone depleting material. I mean, it has a ozone depletion potential, so it is gradually being its use has been reduced significantly now. So uh, so yeah, okay, then let us move on to the problem. So this is essentially a refrigerant. This throttling process is used in the basically used in the vapor compression refrigeration system to cool the refrigerant from the condenser to the evaporator temperature by a throttling process. So this is very essential phenomenon in most of the domestic refrigeration systems and in many in overall in all the refrigeration systems, which especially in the domestic refrigeration system, this throttling process. So this is kind of a, you can say, a practical problem. And regarding this, you said ammonia, right? So ammonia is NH3. So the nomenclature of these materials are such that they are uh, named as R, and then followed by 700 plus the mass of the molecular mass of the substance. That is, if ammonia is what, nitrogen and 3 hydrogen, right? So it is 14 plus 3, that is 17. So it is 700 plus 17. So R 717, that is R 717 is ammonia. Okay. So so there is an entire nomenclature of all of this. How you name the hydrofluorocarbons, the chlorofluorocarbons, and so I think in the future classes you will come to know about this. So let us move on to the problem of discussion in this class today. So it is throttled from 250 degrees Celsius and 750 kPa with a negligible kinetic energy to a pressure of 165 kPa. Okay, we have to determine what is the exit temperature of the refrigerant. Okay, so this is the property table for tetrafluoroethane, that is R134A, and at 750 kilopascal, that is 7.5 bar pressure and 25 degrees Celsius, you can see that the enthalpy value is this and the density value is this. Okay, so for R134A, corresponding to 750 kPa, 7.5 bar, and 25 degrees Celsius, the specific enthalpy, that is the enthalpy, this will be the inlet, right? So enthalpy will be 234.47. This is kilojoule per kg, and the specific volume at the inlet is 1 upon the density at the inlet, that is 1 upon 1208.26. So this comes out to be 0.0000827 meter cube per kg. Okay, so if we write the steady flow energy equation for this throttling device, this heat transferred, again Hi plus Vi squared by 2 plus Gzi, that is equal to W dot plus M dot He plus Ve squared by 2 plus Gz. Okay, so it is said that it enters with negligible kinetic energy. Okay, and also that the velocity remains constant. That means Vi and Ve are same. And if we neglect the potential energy changes, and since there is no heat lost or no work done, so under the assumptions that, not under the assumptions, under the conditions that Q is equal to 0, W is equal to 0, and Vi is equal to Ve, these are the given conditions, and under the assumptions and assuming that the change in the potential energy is nearly equal to 0, we reach that Hi is equal to He. So this is a very important equation for the throttling process. So the throttling process takes into account this phenomenon, that the enthalpy at the inlet and the exit will essentially remain constant. So since the enthalpy remains constant, but the pressure decreases because of the throttling process, so the temperature decreases, and from this condenser temperature, the temperature decreases to a significant level such that the low temperature that we ultimately use for the evaporator of a refrigeration system, that is domestic refrigerator, so it may be 0 or 1 degree, or it may be below that also. So essentially that low temperature is attained by this process. Okay, so it is essentially a very important phenomenon, throttling. Okay, this is this is essentially a characteristic of the throttling process. Okay, so then okay, therefore the enthalpy at the exit is equal to enthalpy at the inlet is equal to 234.47 kilojoule per kg. Now at the exit, what is the condition given at the exit? At the exit, the condition given is 165 kPa. Only that condition is given. So 165 kPa. Okay. The enthalpy of the fluid. Here you can see that in the saturation zone, the enthalpy of the fluid is what? At the fluid state, that is 180.2908, and the enthalpy of the gas is 389.6896. Okay, these two values. Okay, so we can say that the enthalpy of the liquid is enthalpy at the exit state is between these two values. Okay, so that means that this condition is essentially this, which implies therefore the exit state is in the saturation region. Okay, exit state is in the saturation region, and essentially the temperature that corresponds to this saturation pressure will be the exit temperature. Okay, so let us find out what is the quality. So we can find out the quality as He is 1 minus Xe, enthalpy of the liquid, enthalpy of the gas. So the Xe value is He minus Hf by Hg minus Hf. So if we put in all these values, this value and the values, this one, so it comes out to be equal to 0.2587. Okay, and therefore the temperature at the exit stage is therefore temperature at exit stage is equal to the saturation temperature corresponding to T saturation equals to 165 kPa. Okay, so from the property table, we see that corresponding to 165 kPa, the temperature this is the saturation temperature. So the saturation temperature is minus 14.86 degrees Celsius. That is nearly minus 15 degrees Celsius. Okay, so you can see that because of the throttling process, the temperature of 25 degrees Celsius has reduced to a temperature of minus 15 degrees Celsius, which will now be used as the evaporator temperature for the refrigerator. Okay, so this is the significance of the throttling process, and this is essentially option number B. So this is option number B is the answer. Okay, so so was this clear to everybody?
Sir, hello, sir.
Yes.
In the throttling process,
Yes.
enthalpy at the inlet is equal to the enthalpy at the outlet.
Yeah.
And in case of refrigerant, if working fluid is the refrigerant,
Yes.
then outlet temperature is any decrease. Outlet temperature will any decrease.
Yes.
If the working fluid is the ideal gas,
Yeah.
in that case,
Yeah. Yeah. That
temperature
is why in ideal
remain
cases,
constant.
yeah, you go on.
Temperature will remain constant. Yeah, it will any
Yeah, it
decrease.
will remain constant. That is why ideal gas, like you
Uh,
have you heard of,
Sir,
I mean,
yes, in the H1 equal to the H2, SI equal enthalpy is the function of the temperature.
hmm,
Therefore, temperature should remain constant in case of the ideal gases.
Yeah, it will remain constant in case of ideal gas. So I hope that you have not heard that air is used as a refrigerator in domestic refrigerants, right?
Yeah, yeah, sir.
That is the region. That is the reason why
Yeah.
air and other ideal fluids cannot be used, because that there will
Ah,
be no temperature drop. If we there is another class of refrigeration system, that is which we call as the aircraft refrigeration system, which is used in airplanes. Okay, so there air is used, and there the decrease in temperature phenomenon is not throttling. Okay,
yes, sir.
so that the phenomenon is different. So but in throttling process, ideal gases cannot be used for the decrease in temperature. Okay, since
Okay, sir.
R134a is not an ideal gas, so it will, that is why only it will have a decrease in temperature. Okay,
Okay,
so does
okay,
it answer?
thank you, sir.
Okay, so we will move on to the next problem. Okay, so this is a continuation of the previous problem. So in the previous problem, we have to find the ratio of the exit pipe diameter to the inlet pipe diameter. Okay, so okay, at exit, that is 165 kPa. From the table, we can see these the density of the fluid and the density of the gas are given. So the specific volume values can be taken as reciprocal of those values. So the specific volume of the liquid phase is 1342.34, and we are just taking the reciprocal of the density values here. So this comes out equals to 0.000745 meter cube per kg, and the specific volume of the gas, it comes out to be 0.1199 meter cube per kg. Okay, and from the previous problem we had found that the quality at the exit is 0.2587. So what is the specific volume at the, sorry, what is the specific volume at the exit? This will be 1 minus xc Vf plus xc into Vg. So if we put in all these values, we will find that the specific volume at the exit is 0.0316 meter cube per kg. Now, in the entire throttling process, this is a steady flow system and the mass is constant, right? So mass is constant. Okay, this implies AI Vi rho I is equal to AE VE rho E. This is the we are equating the mass flow rates at the inlet and the exit. Okay, so rho I is, again it will be the inverse of the specific volumes. So AI Vi by Vi is equal to AE VE by this value. Okay, so we have to determine what is the ratio of the exit pipe diameter to inlet pipe diameter. So AE by AI is equal to Vi by VE into this value. Okay, now it states that in the problem it was stated that the velocity remains constant at the inlet and the exit. So Vi is equal to VE. Therefore, and this can be written as what? Pi by 4 dE square, and this is pi by 4 dI square. Okay, so this is essentially 1, so this will just be VE by VI, is the ratio of the specific volume at the exit to inlet. So dE by DI, which we have to determine, is equal to pi by 4 gets cancelled, so this will be under root of VE by VI. So if we put in the values 0.0316, and at the inlet we have found out that it is this value 0.000827, 0.000827. So this comes out to be equal to 6.18. So the ratio of the exit pipe diameter to inlet pipe diameter is this. Okay, so I hope this is clear. If it is, then we will move on to the next problem. Okay,
Yes,
yeah,
yes, sir.
yeah, go on.
Okay, sir.
Oh, okay. So fine. Okay. Let me move on to the next problem then. So it is okay. So it is a small expander. Now we from the throttling now we move to a turbine. Okay, it is a small expanding device which takes 0.05 kg per second of helium entering at 100 kilopascal and 500 Kelvin and leaving at 250 kilopascal and 300 Kelvin. Now the power output of the shaft, that is the turbine, is used for a power output, right? So the power output is given as 55 kilowatt, and we have been asked to neglect the kinetic and potential energy changes. We have to find what is the rate of heat transfer to the turbine. Okay, it can be a heat lost from the turbine or it can be a heat transferred into the turbine, and it is given that the specific heat at constant pressure for helium is 5.193 kilojoule per kg Kelvin. Okay, yes, is there any doubt? Is there any doubt? Okay,
No, no, sir.
okay, okay. So this will essentially be capital K, Kelvin, a printing error. So okay, so what are the given data? Given is that the mass flow rate is 0.05 kg per second. Okay, and the work done, sorry, um, so yeah, the work done, this is 55 kilowatt, and the kinetic and potential energy changes are to be neglected. Kinetic and potential energy changes are to be neglected. Okay, so the SFE, the steady flow energy equation, it essentially becomes Q dot plus M dot HI VI square by 2 plus GZI M dot HE plus VE square by 2 plus GZE. Okay, so these are neglected. Kinetic and potential energy changes are neglected. So since we have to determine what is the rate of heat transfer, that is essentially we have to determine what is the value of Q dot. This is equal to W dot plus M dot HE minus HI. So considering Cp to be an ideal gas in which, considering helium to be an ideal gas in which the Cp it does not essentially change with this at this temperature range from 300 Kelvin to 550 Kelvin, we can say that this 55 into 10 to the power 3, and this can be written as m dot and Cp Te minus Ti. Okay, so just put in the values. M dot is 0.05, Cp is 5.193 into 10 to the power 3, and the temperature difference is exit temperature is 300 and the inlet temperature is 550. Okay, so this is essentially 55 into 10 to the power 3 minus this value comes out to be 64.9 into 10 to the power 3. So this is essentially minus 9.9 into 10 to the power 3. Therefore, rate of heat transfer to turbine is equal to minus 9.9 into 10 to the power 3 watt, or you can say it minus 9.9 kilowatt, and this is the negative sign implies that the heat is lost from the turbine. Okay, implies heat lost from turbine. So this is the answer. Okay, so I hope this is clear. This was a very simple problem. If is there any doubt? If there is no doubt, then I will move on to the next problem. Okay, let me then move on to the next problem. Okay, so the mass flow rate, it is also a turbine problem in which the mass flow rate of steam into the steam turbine is 1.5 kg per second, and the heat transfer from the turbine is 8.5 kilowatt. It says the heat transfer from the turbine, that is, heat is essentially being lost from the turbine. Okay, and we have to determine what is the power output of the turbine. The given properties are given at the inlet and the exit conditions. So at the inlet condition, it is 2 megapascal, 350 degrees Celsius, and the velocity and elevation of the given, and at the exit condition, it is 100 kilopascal, and the quality is 100 degrees. Sorry, 100%. That means it is a quality of 100% implies that the condition is saturated vapor, right? We have already discussed when the quality becomes 100%, that it is saturated vapor, and when the quality is 0%, that it means that the state is saturated liquid, and the velocity and elevation are also given here. So the given conditions, so the solution, so the given condition is the mass flow rate is 1.5 kg per second, and the heat loss from the turbine, this is the heat transferred from the turbine, that it is coming out from the turbine, that it is heat loss, so it is minus 8.5 kilowatt. Okay, and at the inlet, the velocity condition is given as 50 meter per second, the elevation is given as 6 meter. Okay, and at 2 megapascal and 350 degrees Celsius, this will essentially be in a superheated region. If we see the property table, then inlet enthalpy will be equal to 3136.96 kilojoule per kg. Okay, and at exit, okay, at exit the velocity is given as 100 meters per second, and elevation is given as 3 meter, and for since the that is x equals to 100% implies saturated vapor state. Okay, so therefore at saturation pressure of the saturation of 100 kPa, the specific volume, sorry, the enthalpy at the exit will be the enthalpy of the gas at that state, and that is equal to 2675.5 kilojoule per kg. Okay, so if we write the SFEE, now SFEE, okay, Q dot plus M dot HI plus VI square by 2 plus GZI is equal to W dot plus M dot HE plus VE square by 2 GZE. So essentially here none of the values are neglected, so we have to actually do the all the values of this SFE are almost known, so we have to determine the power output, that is W. So let us put it here. W dot is equal to Q dot plus M dot, and when here HI minus HE plus VI square minus VE square by 2 plus G ZI minus ZE. Okay, so this is minus 8.5 into 10 to the power 3, and the mass flow rate is 1.5. So if we put in these values, this will be 3136.96 minus 2675.5. This is in kilojoules, so 10 to the power 3 plus Vi square, that is inlet velocity is 50 squared minus 100 squared by 2 plus 9.81 is 6 minus 3. So this is essentially minus 8.5 into 10 to the power 3, and this value comes out to be 686.61 into 10 to the power 3. So this is essentially 678 point, sorry, yeah, 11 into 10 to the power 3. Okay, so the power output of turbine, therefore power output of turbine, sorry, output of turbine is 678.11 is 10 to the power 3, that is in kilowatt it will be, so 678.11 kilowatt. Okay. So is it clear to everybody?
Yes, sir.
Okay, then we will move on to the next part of the problem. Okay, so now this is an air compressor which takes in air at 100 kPa and 17 degrees Celsius and delivers it at 1 megapascal and 600 Kelvin to a constant pressure cooler in which the air exists at 300 Kelvin. So we have to find what is the specific compressor work input. Now at the state 1, this is for air. Okay, so from the property chart of air at 100 kPa and 17 degrees Celsius, the enthalpy value is 290.17 kilojoule per kg. Okay, and at state 2, okay, at 1 megapascal and 600 Kelvin, the enthalpy value for air, it is 607.02 kilojoule per kg. Okay, now if we write the SFEE with heat, this is essentially there is no heat transfer, so Q will be 0, and neglecting the changes in potential energy and kinetic energy, the SFEE will take the form we can see here the SFEE. See, this is 0, and the kinetic and potential energy changes become are also neglected. So W dot will be m dot Hi minus He. So this will essentially be W dot is equal to m dot Hi minus He. Okay, so W dot by m dot, this is equal to Hi minus He. This is 290.17 minus 607.02. This is minus of 316.15. Okay, this negative sign indicates this is essentially a compressor, right? So work will be done into the system, that is the work will be done into the compressor to compress the air. So negative sign, that is work is done on the system, so indicates work done on system. Okay, therefore the specific compressor work input, therefore specific compressor specific means by I mean per unit mass. So specific compressor work input is again, that means it is already taking care of the negative value, so it is just 316.15 kilojoule per kg. Okay, so this is the answer. Okay, and so if this is clear, then we will move on to the next problem. If any of you has any doubt, you can ask. Okay, so if there is no doubt, then let me move on to the next problem. Okay, so it is a continuation of the previous problem, and in the that is, we have to find the specific heat transfer in the cooler. Okay, so for the cooler, you can see for the cooler the inlet is stage 2 and the exit is stage 3. Okay, so the inlet is state 2 and exit is at state 3. So since it is given that it is a constant pressure cooler. Okay, constant pressure. So since the cooler is a constant pressure system, okay, therefore P3 is equal to P2 is equal to 1 megapascal, and at P3 equals to 1 megapascal and T3 is equal to, the exit temperature is given at 300 Kelvin. So at 300 Kelvin for air, the enthalpy value will be 300.19 kilojoule per kg. Now if we again write the SFE, see here the SFE, there is no work, there is heat loss, but there is no work in this section, and the kinetic and potential energy changes are neglected. So SFE with no work done and change in kinetic energy to be 0 and change in potential energy are considered to be 0, then the SFE will become this. Okay, so this is what the mass flow rate is. Oh, we have to find the specific one. So sorry, that is we have to find a specific heat transfer. So this is Q dot by M dot, that is He minus Hi, and He is this one, H3. Just let me write it, H3 minus H2. So this is essentially 300.19 minus H2 is 607.02. So this is minus 306.83. Here the negative sign indicates heat lost from system, from cooler. Okay, which is, it is giving a practical explanation also. It is a cooler and the heat is to be lost, so the heat transfer comes out to be negative. Therefore specific heat lost from the cooler, specific heat lost from cooler is equal to heat loss, so the negative sign is already been taken care of, so 306.83 kilojoule per kg. Okay, so this is the answer. Okay, so is it clear to everybody? If it is clear, then we will move on to the next problem.
Yes, sir.
Okay, Thank you. So this is the last problem of today's session. So it is stated that two steady flows of air entering a control volume. One is at so there are two flows of air. One is at the state 1 and the other is state 2, and they combine here with a given value of heat rejection and some work done by the system, and there it comes out at the state 3. So at state 1, we can see that the M1 is equal to 0.025 kg per second. The pressure P1 is 350 kPa and T1 is 150 degrees Celsius, and corresponding to these values for air, we no, we don't need the enthalpy value right now, so we can just do the problem with a constant specific heat value. So at the state 2, the M2 dot, this is what we have to determine. We have to determine the mass flow rate at the state 2, which is not given, and the pressure at the state 2 is given as 450 kPa, and temperature is given as 15 degrees Celsius. Okay, and at state 3, that is this is essentially the exit state, in which M3, this will be equal to what? This will be the sum of the two masses that it is coming in. The two masses are coming in and it is leaving at state 3. So the combined mass will go out at the state 3. And P3 is equal to 100 kPa and T3 is equal to minus 40 degrees Celsius. Okay, so and this, it is given that the Q rejection is 1 kilowatt, and so it will be minus since it is rejection, and it produces 4 kilowatt of power output. And since it is producing work, so the work is done by the system, that is a positive work. Okay, so if we write the SFEE, now SFEE by, if we neglecting the kinetic energy, kinetic and potential energy changes. The SFEE will become Q dot plus M1 dot H1 plus M2 dot H2. This will be equal to W dot plus M3 dot H3. Okay, so Q dot plus M1 dot H1 plus M2 dot H2. This is W dot, and M3 dot is what? M1 dot plus M2 dot H3. Okay, we have to determine M2, right? So let me take the other, let me separate the values. So M1 dot H1 minus H3 minus W dot is equal to M2 dot H3 minus H2. Now we considering if we thus, just let me write it first. M2 dot, it will be equal to Q dot plus M1 dot, plus Q dot minus W dot plus M1 dot H1 minus H3, and by H3 minus H2. Okay, now assuming constant specific heat for air as Cp equals to 1.004 kilojoule per kg Kelvin, we can write M2 dot as q dot minus w dot plus m1 dot cp t1 minus t3 and cp t3 minus t2. Okay, so what is q? So if we put in the values from here, it will be minus 1, q is minus 1, minus, and w is 4, so minus 4. These are in kilowatts, so and since cp is also in kilojoules, so we are not writing the 10 to the power 3 term here. So and I mean there will be a 10 to the power 3 in this, and there will be a 10 to the power 3 in this, so the 10 to the power 3, 10 to the power 3 gets cancelled, so we don't need to write that. So m1 dot will be 0.025 into cp is 1.004, t1 minus t3, so t1 minus t3 is 150 minus t3 is minus 40, so it is minus 40. Okay, and this is 1.004 into t3 is minus 40 minus t2 is 15 degrees. Okay, okay, so we have not written the 10 to the power 3 terms. I hope this is clear, because there will be a 10 to the power 3 in the numerator also and in the denominator, so they get cancelled. So this is basically minus 5, and this value comes out to be 4.769, and this will be 1.004 into minus 55. Okay, so by simplification this value comes out to be 0.0042. Therefore the mass flow rate of the at state 2, mass flow rate at state 2 is 0.0042 kg per second. Okay, this is the answer. So are all of these clear to you?
Yes, sir.
Okay, so essentially we have reached the end of today's session, and I hope the concepts were clear. So yeah, so if you have no more doubt, you can leave the session.
Thank you, sir.
Okay, thank you very much. Please visit in the next session so that we can solve the questions and the week 6 questions. Okay, so thank you.